Hello, workload 910 students. Here is the video meant to accompany homework number 3, logarithms. So, what is a logarithm? Well, essentially, a logarithm is an exponent. If you had an equation like b to the y equals x, that would be equivalent to writing log base b of x equals y. It's not a great example, though. Let's use a numerical example. My favorite is this one. 2 to the third is equal to 8. As a logarithmic equation, so I would say this is an exponential equation. The equivalent logarithmic equation is, well, this is a base of 2, so it's log base 2 of 8 is equal to 3. So we can rewrite logarithms as exponential equations. We can rewrite exponential equations as logarithmic equations. When I look at this, I kind of think of it as, here's my base. I do like to say base 2. I think of it being raised to that power over there. And then the whole thing is equal to that number inside the logarithm, or the argument of the logarithm is what the whole exponential thing is equal to. Another thing I'll say, just because I like to say it a lot, is when I read something like log base 2 of 8, I'm going to write this over here. When I write something like log base 2 of 8, log base 2 of 8 means, or the words I say in my head are 2 raised to what power, the power is what we're looking for, the exponent if you prefer, equals 8. So whenever you see log base something of something, like log base 2 of 8, you should ask yourself, oh, the base raised to what power equals the argument? In this case, the answer would be 3. I also want to point out here that we can always rewrite logarithms as exponential equations. Sorry, the line's not very straight there. And vice versa. We can always rewrite exponential equations as logarithmic equations. I say I said logarithms, not logarithmic equations, but we'll talk about that when we get to that section. So first part here, we're going to solve some logarithmic equations. So I want to solve log base 7 of n is equal to 2. There's a couple ways to go about this, but I think the most typical way is just to rewrite it as an exponential equation. My base is 7, my exponent is 2, or my power is 2. It's equal to n. So that's going to give me n equal to 7 squared, which is 49. That's it. Easy peasy. So then, same deal here. I'm going to solve this logarithmic equation by rewriting it as the base raised to the exponent equal to n. Technically, you could leave it like that, but I really think we should simplify these. So I'm going to write this as 3, I should say 1 over 3 to the positive fourth is equal to n. And then 3 to the fourth is 3 times 3, which is 9, times another 3 times 3, which is 9, which is 9 times 9, which is 81. So we have 1 over 81 equal to n. Cool. A few of these I forgot to write the word solve on them. Apologies. So for this third one here, to solve log base 64 of n equal to 1/3, we're rewriting this logarithmic equation as an exponential equation. So I'm going to write it as a base of 64 raised to the 1/3 power equals n. You might just know that the cube root of 64 is equal to 4. You might not. Another way to see this is to say, oh, well, I know that 64 is 4 to the 3rd power to the 1/3 power. And then when you have a power to a power, you multiply the powers. So we end up getting that 4 to the 3 times 1/3 is equal to n. 3 times 1/3 is 1, so 4 to the 1, which is just 4, is equal to n. You don't have to show all that work here. It's perfectly fine to just say, hey, 64 to the 1/3 equals n, so n equals 4. That would also be totally fine because I think it's reasonable to say that you could know what the cube root of 64 is without showing any other work. Okay, some more of the same stuff. We're going to rewrite this logarithmic equation as an exponential equation. So I would read this as log base 8 of n equals 4/3. I'm going to rewrite this as the base 8 raised to the power of 4/3 is equal to n. You could also put the n on the left-hand side. It doesn't matter, right? I could also just as easily write it as n equal to 8 to the 4/3. I know that might feel better to some people because we like to write like the unknown thing we're solving for on the left-hand side. Doesn't really matter. So then I'm always, or almost always, when I'm dealing with a fractional exponent, I'm going to do the root part first and the power part second, or I should say the denominator part first and the numerator part second. So I'm going to think of this as 8 to the 1/3 to the 4th. 8 to the 1/3 is the cube root of 8. You could skip writing that though if you wanted to. You don't need to rewrite a fractional 1 over something power as the something root, but you can. Cube root of 8 is 2. 2 to the 4th is 2 times 2 times 2 times 2, which is 16. You also could have just gone straight from here to there, skipping this step and wrote it like that. This one looks a little bit wonkier, but still the same idea. We have log base square root of 5 of n equal to 6. I didn't write the n in parentheses, it's fine. So I'm going to rewrite this as the base square root of 5 raised to the 6th power equal to n. And then I'm going to simplify this. So the square root of 5, I do want to write this as 5 to a power. So the square root is the same as the 1/2 power, just like the cube root is the same as the 1/3 power. And the 4th root is the same as the 1/4 power. But we have to be careful because like when I say the 4th root, you might hear like the 4th power. So when I say the 4th root, I really mean the 1/4 power. Excuse me. So I really need to be careful with my language there. So I'm going to rewrite this as 5 to the 1/2 to the 6th equal to n. But then when we have a power to a power, we can multiply those powers. That's going to be 5 to the 1/2 times 6. 1/2 times 6 is the same as 1/2 of 6, which is 1/2 of 6, which is 3. That's going to be 5 to the 3rd equal to n. And 5 to the 3rd is 125. So we get n equal to 125. Moving along. Evaluating logarithms. So this next section is really the same as the previous one. It's just, instead of writing it as an equation to start off with, I'm just saying, find the value here. So there's really two ways you could do this. You could say, I know the answer. I know that I'm trying to find 5 to what power equals 25. And I know that 5 squared equals 25. So I know that log base 5 of 25 is equal to 2. And that's a totally reasonable way to say the answer is 2. You could just say 2. On the other hand, you might not know the answer right off the top of your head, and that's totally fine. If that's the case, what I recommend is making it into an equation. So I'm going to first write it as log base 5 of 25 is equal to the number I'm trying to find. I usually call it x, but any variable is fine. Then we're going to rewrite it as the base raised to the answer equal to the argument. At this point, I think it's really clear that x is 2 because 5 squared is 25. But if you like, you can take one more step here and rewrite both sides as powers of the same base. So if you have two expressions where both are powers of the same base, for them to be equal, the powers have to be equal to each other. The only way 5 to the x is equal to 5 squared is if x is equal to 2. 5 to any other power won't equal 5 squared. Same idea here. This one to me, I feel like is less obvious. So I'm just going to start off by saying, well, let's call it equal to, let's use a different letter for the fun of it. Let's call equal to y. Then we're going to say that 4 to the y is equal to 1/16. That's my equivalent equation. And then I'm going to rewrite both sides as powers of the same base. So I'm going to recognize that 16 is 4 to the 2nd. And then 1 over something is the reciprocal of that something. So it's really that something to the -1. So you can say here, y was probably a bad choice because my y's kind of look like 4s. Sorry about that. Try to make them look very different. 4 to the y is equal to 4 squared to the -1. Or if you prefer, 4 to the y equals 4 to the, well, 4 to the 2 to the -1, you multiply those powers and you get -1 times 2, which is -2. So here we should get y equals -2. I suppose to finish off the answer, it's probably best to go back and say, like, I mean, it's okay to leave this as x equals 2, but I might rewrite my final answer as log base 5 of 25 is equal to 2. Or here I might go back and say, well, yes, I said this was y and I got y equal to -2, but it feels kind of better to write it as log base 4 of 1/16 is equal to -2. And that's true because we know that 4 raised to the -2nd power is equal to 1 over 4 squared is equal to 1/16. That checks out. You don't have to check your work like that. I'm just doing it to really show you, oh, yeah, things are true. All right, I have a few more examples. They get a little bit more challenging. Log base 13 of 1. 13 to what power equals 1? Well, the nice thing about 1 is the answer, if a 1 is your argument, the answer is always going to be the same. So, but let me just remind you, if I say this is equal to x, I'm going to rewrite this as 13 to the x equals 1. When you raise something to a power and you get 1, the power had to have been 0. So this is true because 13, or okay, so this is only true when x is equal to 0, because 13 to the 0, just like 5 to the 0, just like 7 to the 0, just like any non-zero number raised to the 0th power is equal to 1. So this means here that x has to equal 0. So I would say that log base 13 of 1 is equal to 0. And I would say it doesn't matter what your base is. I could have said log base 5 of 1, log base 27 of 1. Any base that's a normal base, meaning not 0, not 1, not negative, is equal to 0. Technically, it would be true for negative bases, but we don't like negative bases because they make for weird functions. So we prefer positive bases that are not equal to 1. In fact, we kind of require that. All right, log base 4 of 32. Same deal. I don't know. So I'll point out here the answer is not 8. Right? 4 times 8 is 32, but I'm asking 4 to what power or what exponent is equal to 32. So to do that, I'm going to rewrite this log base 4 of 32 equal to, let's pick the letter A. It's good to use different variables sometimes, although really x is the normal choice, the standard choice. We're going to rewrite this as 4 raised to the A power equal to 32. And then we want to write both sides as powers of a common base. Well, 4 and 32 are both powers of the number 2. 4 is 2 to the second, 32 is 2 to the fifth. So we're going to rewrite both of these as powers of 2. So 2 to the second to the A equals 2 to the fifth. On the left-hand side, power to a power, we multiply the powers. So you have 2 to the 2 times A equal to 2 to the fifth. And then when you have an equation where the bases are the same, it must be true that the powers have to equal each other. There's no way that these are equal unless that power there is equal to 5. So you get to say 2 times A is equal to 5, which means A is going to equal 5 over 2. Or if you prefer 2.5, although I prefer fractions almost exclusively. Maybe not exclusively, but pretty closely. And then I would probably go back and say, so that means log base 4 of 32 is equal to 5 halves. Probably not super necessary, but not worthwhile. All right, let's take a look at this one. Yeesh. Yeah, that's quite looking gross there. So I would still do the same thing. I'm going to point out how you can get away with not doing the same thing here. So in fact, actually, let me just point out, if someone asked you what log base 6 of 6 to the 7th power is, they're really saying 6 to what power equals 6 to the 7th power. The answer maybe to me seems obviously like it has to be 7. But if you set this equal to x, you can say, well, 6 to the x has to equal the inside, which is 6 to the 7th. And the only way that works is if x equals 7. The same thing is true here. We just have to rewrite the argument here. So you can rewrite this as log base 5 of, so I'm going to fix this here. So I'm going to say that's the cube root of 5 times 5 to the 1/2. 5 to the 1 times 5 to the 1/2. You add the powers, you get 5 to the 3/2. That's the same as log base 5 of 5 to the 3/2. Sorry. So it's really the cube root of 5 to the 3/2. Let me squeeze that in there. It's kind of terrible, but I think I can make it work. And then the cube root is the same as being raised to the 1/3 power. So we can say this is equal to log base 5 of 5 to the 3/2 to the 1/3. Power to a power, you multiply the powers. 3/2 times 1/3 is 3 times 1 over 2 times 3, which is 3 over 6, which is 1/2. So you have log base 5 of 5 to the 1/2. And then you can say, well, just like log base 6 of 6 to the 7 had to be 7, log base 5 of 5 to the 1/2. You're asking, what power do you raise 5 to? So you end up getting 5 raised to the 1/2. Well, the seemingly obvious answer is 1/2. Or again, if you don't like just jumping to that, you could say, well, I'm gonna still do the same simplification, right? I'm gonna say that I have log base 5 of 5 to the 1/2, and if I set that equal to x, that's equivalent to saying 5 to the x is equal to 5 to the 1/2. Oh, x has to be 1/2. There's no other choice. But when your base here and the thing you're taking the logarithm of have the same base, it's really easy to see that the power on this base is your answer. Or at least after some practice, it becomes easier to see that that's the case. All right. Sometimes we do something weird, I think, and we have a solve for the base. I feel like this is atypical, but it's something we do. I should point out that for logarithms and for exponential functions later on, the base should be positive and not equal to 1. Again, negative bases aren't impossible. They just have weird repercussions when you start looking at the logarithm as a function. We would rather not have to deal with those. So you should make the assumption that your answer should be a positive number, and it will almost never be 1, because if you have log base 1, you're saying 1 to some power equals something else, but 1 to any power is always 1, so you could really almost never solve it. All right, so again, solving these is really just going to be an exercise in rewriting it as an exponential equation. So I'm going to rewrite this as my base, which is x to the power, which is 3, equal to 8. And then I could know the answer, or I could try to isolate x by raising both sides to the reciprocal power. So if I have x to the third equals 8, that's the same as x to the third to the 1/3 equals 8 to the 1/3. X to the third to the 1/3 is x to the first, which you could and should just write x. Cube root of 8, you could just say is 2, or you could say, I'm going to rewrite it as the cube root of 8 because it makes me feel better. And then finally, we get x equal to the cube root of 8, which is 2. So now I would just say x. I would leave it like that. I wouldn't go back and be like log base 2 of 8 equals 3. Same kind of deal here. We're going to rewrite this as x to the negative third equals 125. And you might recognize the 125 is 5 to the third power. It might actually help to write that. We'll see. So again, I'm going to do the same thing to both sides. I'm going to say x to the negative third. The reciprocal of -3, the reciprocal of any number is just 1 over that number. So you can either write this as 1 over -3, or I would prefer to write it as -1/3. They're the same number. That's going to equal 125 raised to the -1/3. -3 times -1/3 is +1. So the left-hand side becomes x to the 1. And the right-hand side, there's a couple ways to deal with this. One way to deal with it would be to say, well, that's going to be 125, I mentioned earlier, was equal to 5 to the third. So I'm going to rewrite this as 5 to the third to the -1/3. Power to a power, you multiply the powers. 3 times -1/3. If you really like, you write it as 3 over 1 times -1/3. And then 3 times 1 is 1. 3 times 1 is what? 3 times 1 is 3. 1 times 3 is 3, but there's a negative out in front, so it's -3 over 3, which is -1. So this becomes x equal to 5 to the -1, and 5 to the -1 is the same as 1 over 5 to the first, or just 1 over 5. So x is going to equal 1/5. An alternative way to get there is we could have said, I want to rewrite this as x equal to, right, because this is, again, x to the -3 to the -1/3 is just x. 125 to the -1/3. I often like to just deal with the negative power by rewriting it as 1 over the same thing to this corresponding positive power. That's going to equal 1 over the cube root of 125. And with practice, we get to know that the cube root of 125 is just 5. Oh, look, we got the same answer. Either way is fine. A few more kind of funkier ones. So here we're solving log base x of 4 equals 2/3. We're rewriting as our base raised to the 2/3 power equal to 4. Almost every time when you're solving for a base, you're going to rewrite it as an exponential equation, and then you're going to raise both sides to the reciprocal power to get the x isolated. Positive numbers always have positive reciprocals. So the reciprocal of 2/3 is 3/2. Negative numbers always have negative reciprocals. We'll see that in the next example, so we'll get there. So I'm going to raise both sides to the 3/2 power. So I'm going to have x to the 2/3 to the 3/2 equals 4 to the 3/2. X to the 2/3 to the 3/2 is x to the 6/6, which is just x to the 1, which is just x. You don't need to write that. 4 to the 3/2, though, I would strongly recommend breaking up as 4 to the denominator part first, so 4 to the 1/2 to the 3rd. You end up with x to the 1st equal square root of 4, which is 2 to the 3rd power. So x equals 8. Cool. Similar deal here. We're going to rewrite this as our base, which is x, our exponent, which is negative 3/4, equal to our argument, which is 1 over 27. And then we're automatically, first thing trying to solve for x, I'm going to raise both sides to the reciprocal of negative 3/4, which is negative 4/3. So I'm going to have x to the negative 3/4 to the negative 4/3 equal to 1 over 27 to the negative 4/3. Yeah. Kind of annoying over here. The left-hand side is just x to the 1st, right? Negative 3/4 times negative 4/3 is positive 12 over 12, which is positive 1. So we have x to the 1, which is just x. Over here, there's a lot of different things you could do first. The thing I would prefer to do is rewrite 1 over 27 as 27 to the negative 1. So one option is to say this is 27 to the negative 1 to the negative 4/3. And then the power to a power is power to power, you multiply the powers. So you could say that this is x equal to 27 to the positive 4/3, because the negative times the negative is positive. Then we can say we get x equal to 27 to the 1/3 to the 4th. The cube root of 27 is 3, still raised to the 4th power. And 3 to the 4th, we've seen before, is 3 times 3 times 3 times 3, which is 9 times 9, which is 81. But maybe you didn't want to do it this way. Maybe rewriting 1 over 27 as 27 to the negative 1 just doesn't feel natural. So another way you could have gone would have been to have said, let me box this center first. You could have treated this as, well, when you have a fraction to a power, each part gets raised to that power. So you can say this is 1 to the negative 4/3 divided by 27 to the negative 4/3. 1 to any power is 1. Right? Because you're saying 1 times 1 times 1 a bunch of times, or the root of 1 or the cube root of 1, all those are 1. Fun fact, 1 to any power is 1. So this is going to be 1 over 27 to the negative 4/3 power. And then I would immediately get rid of the negative power by writing this as 27 in the numerator raised to the positive 4/3 power. And then we're on the same journey as we were over here. That's going to be 27 to the 1/3 to the 4th, which is 3 to the 4th, which is 81. So there's a few different ways to go here. We're almost done solving for x in an exponential equation. So, and we're going to solve these under the assumption that we don't have any kind of logarithmic rules yet that we'll talk about soon. We're just going to use rewriting exponentials as logarithms. So here I have the base of 2 raised to the x minus 1 equals 9. I'm going to rewrite this as log base 2 of 9 equal to x minus 1. So whenever you're rewriting an exponential equation as a logarithmic equation, the base here and the base here should be the same. And the logarithm, the log base 2 of whatever, should be equal to whatever the exponent is here. So 2 to the x minus 1 should equal 9. Oh yeah, 2 to the x minus 1 equals 9. So those are the same. And then isolating x is really easy. We're just going to add 1 to both sides. So we're going to get that x is equal to 1 plus log base 2 of 9. And there's really nothing more you can do to simplify this. Not without using a change of base formula, which we're not really talking about just yet. Same deal here. We're going to rewrite this as a logarithmic equation. So our base is 5, and the exponent is 3x minus 1, which means we should have log base 5 of something equal to the exponent 3x minus 1. Specifically, it's log base 5 of 7, right? 7 is the only other piece there, equals 3x minus 1. And then we're going to solve for x. We're going to add 1 to both sides. So we're going to have 1 plus log base 5 of 7 equal to 3x. The reason I put the 1 in front here as opposed to like writing log base 5 of 7 plus 1 is sometimes people write that and they accidentally add the 7 and the 1 together, which is not allowed, right? The 7 is, you have to take the logarithm of it first before you add the 1 to it. So then if we divide both sides by 3, we're going to get 1 plus log base 5 of 7x, all divided by 3 equal to x. Or if you prefer, you could divide each thing individually by 3 and say x is equal to 1/3 plus log base 5 of, I don't know how an extra, sorry, let me back that up a minute. There's an extra x there for no good reason. It should be 1 plus log base 5 of 7, all divided by 3 is equal to x. Or x is equal to 1 divided by 3 plus log base 5 of 7 divided by 3. Important to know, when you're writing your answer as x equal to something, there should not be any x's in your answer. So that x there is definitely off base. Let me rewrite it here just so it looks nicer. Here you would have x equal to 1 plus log base 5 of 7, all divided by 3. Well, it's a little bit better than that. Cool. Lastly, good to know how to approximate values of logarithms, specifically what numbers they're between. So this is kind of similar to saying, like, if I said, for a different example, the square root of 13. What two numbers is that between? Well, we know the square root of 13 is less than the square root of, well, the next biggest number that's a square number is 16. The next smallest number that's a square number is 9. So 13 is, sorry, the square root of 13 is certainly between the square root of 9 and the square root of 16, but the square root of 9 is 3, and the square root of 16 is 4. So it's clear the square root of 13 is between 3 and 4. And if you get out a calculator and take the square root of 13, you'll get 3 point something, something, something. In a similar way, we can find what two numbers of log base 2 of 11 is between. So let's just start writing log base 2 of nice numbers. Like log base 2 of 2 is equal to 1, because 2 to the first power equals 2. And log base 2 of 2 squared is equal to 2, because 2 to the second equals 4. And log base 2 of 2 to the third is equal to 3. And log base 2 of 2 to the fourth is equal to 4. And somewhere in between there is log base 2 of 11, right? 11 is between 8 and 16. So log base 2 of 11 is between log base 2 of 8 and log base 2 of 16. So I kind of came up with this on the fly. It's coincidental that they both happen to be between the same two integers, but it's true that log base 2 of 11 is less than 4 and bigger than 3. Because 4, again, is the log base 2 of a bigger number, and 3 is the log base 2 of a smaller number. Same idea for this last one here. Log base 5 of 100. Well, let's write down some more convenient numbers. So I want to think about powers of 5. So 5 to the first is 5. 5 squared is 100 is 25. 5 cubed is 125. And just for fun, even though we don't need it, 5 to the fourth is 625. So then it's true that log base 5 of 5 is 1. And log base 5 of 25 is 2. I'm going to leave myself some space here. Log base 5 of 125 is 3. Log base 5 of 625 is 4. And between 25 and 125 lives 100. So the log base 5 of 100 lives between 2 and 3. So I would write as my answer, the log base 5 of 100 is bigger than 2, less than 3. I would encourage you to check both of these out on a calculator. Well, maybe a fancier calculator where you can change the base. So there is a way to do this without using the log base 2, which we'll talk about next time. That is all I have for this video. I hope that it was educational.